Every aspect of modern life relies on a physical tether. We pull raw power from the electrical grid through solid copper wires plugged directly into our walls. But place a modern smartphone down onto a sleek wireless charging pad, and that physical tether is instantly severed. Usually, breaking a physical circuit yields an immediate, violent stop to the flow of electricity. The raw power has nowhere to go. The charging pad has to somehow push that exact same electrical energy across a physical void without generating enough uncontrolled heat to destroy the lithium-ion battery inside the device. You're watching a continuous, invisible dialogue between two autonomous machines, running entirely on laws of physics mapped out over a century ago. The journey begins the moment standard direct current enters the pad from your wall outlet. The conversion circuit forces flat direct current to rapidly reverse, turning it into alternating current. Pushing through the transmitter coil creates a pulsing magnetic field. When your phone enters that field, the waves push against a second coil, forcing new electrical current to flow. Physicist Michael Faraday documented this exact mechanism, known as electromagnetic induction, in the 19th century. A changing magnetic field generates electricity in a nearby conductor. But standard induction has a severe physical limit. It demands exact point-to-point alignment to maintain the flow of power. Shift that phone even slightly off-center, and the magnetic field breaks, halting the charge immediately. Engineers bypassed this rigid physical constraint by introducing magnetic resonance. Strike a tuning fork, and it emits kinetic energy. A second fork tuned to the same frequency captures it, vibrating independently. Applying that resonance to electromagnetism expands the distance. Tuning the charger and phone to the same frequency bridges a much wider physical gap. That simple frequency alignment turns a fragile, highly localized spark into a stable spatial field of energy. Moving power through the air guarantees a loss of efficiency. That lost energy converts immediately into electrical resistance, which manifests as heat. Left unchecked, this thermal runaway would permanently degrade the chemistry of the smartphone's battery. The solution is a hidden layer of machine data transmitted continuously alongside the raw power. The smartphone reads its internal temperature and battery levels, firing a high-speed data stream back into the charging pad. The Qi standard uses this telemetry to tell the pad to instantly throttle its power output down to safe levels, or increase it. These two machines are rapidly negotiating their mutual survival in real time. That combination of resonant power and continuous data transmission is already scaling far beyond consumer accessories. Medical engineers use it to keep life-saving implants permanently sealed inside the human body, eliminating the need for dangerous surgical battery replacements. On factory floors, automated robots pull kinetic energy directly from the ground beneath them, while electric vehicles begin to charge dynamically while parked in a garage. Over a century ago, Nikola Tesla envisioned a completely wireless civilization, attempting to broadcast raw electrical power through the atmosphere on a massive scale. Every glowing charging pad sitting on a nightstand today is a working prototype for an untethered electrical grid.